Now we'll look at an application of sorting from the field of computational geometry for an interesting computation. If you have a set of n points in the plane, there's a geometric object called the convex hull, which is the smallest polygon that encloses all the points. There's the convex hull for that set of points. There's a lot of equivalent definitions of this, some of them very mathematical that extend to higher dimensions. It's the smallest convex set that contain all the points, the smallest area convex polygon enclosing the points. It's a convex polygon that encloses the points whose vertices are points in the set. Those are all equivalent definitions. And what we want to do is, given a set of points, we want to have a program that can give us the convex hull. Now, what should the output of such a program, such a method be? Well, in order to be able to work with the result, it should be a sequence of vertices that gives us that polygon if we follow it. If we've got some points that are on the boundary but aren't really vertices, they shouldn't be included. This points out examples of how difficult computational geometry can sometimes be, because degenerate cases like this are difficult to deal with in code. We're not going to spend a lot of time on this in this lecture, but it's something always to be aware of when trying to apply simple algorithms in situations like this that turn out to be maybe more sophisticated than we might think. Oh yeah, gotcha. Mm-hmm. Well, there's actually a way to compute the convex hull just mechanically. If you put nails around the points and put a rubber band around it, that gives you the convex hull. Now, we're not going to be able to really implement that in a computer program, but it's surprising how well we can do. Here's an application where people want to compute the convex hull. Suppose you have a robot that wants to get from S to T, and there's an obstacle that's defined by some polygon. You want to be able to go around the obstacle, and it turns out that the shortest path, either it's a straight line from S to T, or it's part of the convex hull. And it's not hard to see why that might be true. There's plenty of other applications where people want to be able to compute the convex hull. Here's another application. If you want to find the pair of points that are the farthest apart in a set of points in the plane, this is sometimes important in statistical calculation or other applications. They're on the convex hull. If you have the convex hull, this computation is easy. They're going to be extreme points on the convex hull. So there's a lot of geometric properties of the convex hull that we can take advantage of to develop an algorithm. And here are two properties. Now, these are things that have to be proven, and we're not going to get into the details of geometric proof, but they're intuitive, and you'll certainly have no trouble accepting that these things are true. One thing is that you can traverse the convex hull by making only counterclockwise turns, or left turns if you're looking at the screen here. And the other thing is that, so if we travel from P to point 1, then we make a left turn to go to point 5, or a counterclockwise turn, and then from there we go to point 9 and 12, and then we eventually get back to the start point. The other thing is, if you take the point with the lowest y coordinate, and then if you look at the polar angle with respect for every other point with respect to that one, so the angle you get from the x-axis through P up to the point, then the vertices appear in increasing order of that angle. And again, that's not difficult to see that that's a fact. And the algorithm we're going to look at, called the Graham scan, is based on those two facts. It's the idea is to start with point P, the one with the smallest y coordinate, sort the points by polar angle with P. That is, we're just going to consider them in that order. And then we'll just throw away the ones that do not create a counterclockwise turn. And you'll see how that works when we look at a demo. So we start at point P, sort the points by polar angle with P. So that is, if we take a vertical line and sweep it in a counterclockwise direction, what order do we hit the points? The first thing we hit is 0, 1, and then if we sweep counterclockwise, we get to 2, and then 3 and 4, and so forth. So that's the ordering of those points. And so now we'll just consider those points in order and then take them for the convex hull. At the beginning, 0, 1 is a line that's on the convex hull. So the point with the lowest y-coordinates on the convex hull, and so is the one that is the smallest polar angle it creates with the x-axis. So now what about this one, 2? Is that on the convex hull? Well, as far as we know at this point, it could be. It could be that the thing is a triangle and 0 is the last point, in which case it would be. But it's same with 3. As far as we know, that one could be on the convex hull. But as soon as we go out to 4, that's not a counterclockwise turn. It's going the wrong way. And essentially what this means is that point 4 is evidence that there's no way that point 3 can be on the convex hull. You can convince yourself of that quite easily. So we just throw point 3 out. It's not on the convex hull. So, and what about the angle from 1 to 2 to 4? That's not counterclockwise either. That's turning the wrong way. That's turning to the right. So point 2 can't be on the convex hull either. And indeed, if you just draw the line from 1 to 4, you can see the 2's inside. So there's no way it could be in the convex hull. That's essentially the proof that you have to have a counterclockwise turn. So now we go on to 5, turning the wrong way. So point 4 can't be on the convex hull. So now we go to 6. As far as we know, it could be, but as soon as we hit 7, we know that it can't be because that's a right turn. So 6 is not there. We go to 8. Nope, 7 can't be on the convex hull. Go to 9. 8 can't be on the convex hull. Now we go to 10 and 11. As far as we know, they could be. If 12 weren't there, they would be. But as soon as we hit 12, we see that 11 can't be on the convex hull and 10 can't be on the convex hull. And that completes the computation of the convex hull with the Graham scan. Okay, so there are a number of implementation challenges for the Graham scan, and we're not going to go into detail on these because this is a lecture on sorting algorithms, not computational geometry. But it is indicative of how, even if we have a good sort, we might have to do some extra work to actually solve our problem in an application. So how do we find the point with the smallest y-coordinate? You could sort. You could define an order and compare the points by y-coordinate. So essentially sorting is the answer to that question. And we'll look at the next lecture of what it means to define ordering among objects, a little more general than what we do for sorting. How to sort the points by polar angle. Well, again, we need to define what we mean when we're comparing points. And in the next lecture, again, we'll look at ways to define different orderings among points. And Graham scan's a perfect example. We don't want to just be able to sort things. We don't want to just be able to sort them by defining a compare to. We want to be able to sort the same things in different ways sometimes. And this example is a fine motivation of that. Figuring out whether what we have is a counterclockwise turn, that's a little exercise in geometry, and we'll just talk about that briefly on the next couple of slides. And then, what about getting the sort done efficiently? Well, we could use shell sort, but actually in the next couple of lectures, we'll look at classical sorts, merge sort and quick sort, that we could use. The idea, though, is that this example illustrates that a good sorting algorithm gives us a good complex hull algorithm. That's an extremely important principle in designing good algorithms. Once we have a good algorithm, if we have another problem, we can say to ourselves, well, we've got a good solution to this algorithm. Can we use that solution to solve our new problem? Convex hull, when we have a good sorting algorithm, it gives us a good convex hull algorithm, because the most work in convex hull is the sort. And then again, there's all kinds of difficulties in implementing convex hull in real-world situations because of various degeneracies. And these things are covered on the book site. So the main part of computation that we haven't really talked about, and we'll cover briefly, is if we have 3 points, A, B, and C, and you go from A to B to C, are you making a counterclockwise turn or not? So in the example at the left, A to B to C is counterclockwise. The example at the right, A to B to C is not counterclockwise. If you're going from A to B, you turn left to get to C in the first case, and you go right to get to C in the second case. And we want to do a computation that distinguishes this. Now, this computation would be pretty easy, except for the degeneracies, is what do you want to count it if they're all on the same line? Or if the slope is infinity. So you have to just be aware that these situations have to be dealt with. So the code isn't quite as simple as you might come up with in the first instance that you try. So there's degeneracies to deal with and floating point precision. But researchers in computational geometry have worked this out. And actually, there's not that much code at all in the end involved. And this is a slide that gives the math. And I won't talk through this math. If you're interested in implementing this, you can come back to this slide. And it's essentially based on the idea of computing the slopes of the lines between A and B and between A and C and comparing them to decide whether you're turning counterclockwise or clockwise. And this is the specific math that gets that implemented. This is if we implement a point data type for computational geometry, it can have a method, CCW, that just with this little math calculation, b dot x minus a dot x times c dot y minus a dot y minus b dot y, this calculation here gives you immediately whether it's counterclockwise, clockwise, or collinear. Not much code at all. And that method is the basis for the Graham scan. The Graham scan uses a sort where we give 2 different ways to sort the points, and it uses a push-down stack for the hull. It puts the points on the hull, and it goes ahead and for every point, considering them in the order of the polar sort, it'll compare whether the top 2 points on the hull and the new point implement a CCW turn or not. And if it's not a CCW turn, it pops it and continues going. Very little code to implement the convex hull, given that you have a sort. And that's our main point for this lecture. There's many natural applications of sorting, but also we'll be able to develop new algorithms that use sorts that gain efficiency because of the efficiency of sorting.